Hello, everyone. My name is Katie Gamanji, and currently I am the ecosystem advocate at CNCF. I have joined CNCF last year, and my responsibility is to lead the end-user community while bridging the gap between the end-user organizations and the projects within the ecosystem. I have many roles within the community, and one of them is being a member of the advisory board for Captain, which currently is a sandbox CNCF project. As well, I am collaborating with OpenUK to make sure that open standards are used across data, software, and hardware. And as part of my motivation to make cloud native ubiquitous, I have collaborated with Udacity to create the Cloud Native Fundamentals course. Pretty much this course is constructed to take anyone with little programming experience on the path and journey towards cloud native. I have mentioned the end user community, and I'd like to give a bit more details of what it actually represents. The CNCF end user community currently is constructed of more than 145 vendor-neutral organizations that use cloud native to build and distribute their services. It is the largest end user community out there, and it's at the CNCF's goal of end user driven open source. Pretty much we are looking at these organizations to define the production experience, but at the same time to shape the organic growth of the projects within the ecosystem. If you'd like to find out more details about the end user community and their usage of cloud native, visit the cncf.io/end user. As well, if you'd like to showcase your adoption of cloud native, you'll find all of the details here of how can you join the end user community. Today, however, I would like to talk about GitOps, but more importantly, how it unlocks the infrastructure provisioning and application propagation towards the edge. And to do so, I would like to start by introducing the cloud-native GitOps tools. And here I'm going to give a brief introduction of tools such as ArgoCD and Flux. However, I would like to transition into using GitOps to more real case scenarios, such as infrastructure provisioning, when I'm going to talk about the ClusterAPI and FluxCD integration, and how can we push the applications towards the edge by using the association between KubeEdge and ArgoCD. Before I move forward with the topic, I would like to introduce the ecosystem that allowed this new GitOps model to be constructed or to be identified within the community. If we look 7 years ago, the container orchestrator framework space was very heavily diversified. We had tools such as Docker Swarm, Apache Mesos, Kubernetes, CoreOS Fleet, and all of them provided a viable solution to run containers at scale. However, Kubernetes took the lead in defining the principles of how to run containerized workloads. Nowadays, Kubernetes is known for its portability and adaptability, but more importantly, for its approach towards declarative configuration and automation. And we can see this represented in numbers. Based on the CNCF survey last year, more than 83% of the companies are using Kubernetes in production. When we transition towards the contributor community, more than 2,500 engineers are actively collaborating towards feature build-out and bug fixing. And when we look into the end-user community, more than 41,000 attendees were registered at the KubeCons around the world. Now, these were the KubeCon virtual in Europe and North America. And this has been extremely beneficial for Kubernetes because over time, multiple tools were built around it to extend its functionalities. And this created what today we know as the Cloud Native Landscape, which resides under the CNCF umbrella or Cloud Native Computing Foundation. Now, currently, the CNCF landscape provides a lot of tools that enables further functionalities or integrations. However, the community focused into enhancing the developer experience, but more importantly, introducing a new way or redefining the way we deploy cloud-native components. And this is how the GitOps model came to be about. When we refer to GitOps, pretty much it is a strategy that uses Git repositories as the source of truth for defining the desired state of the application. By using this model, by default, we're going to have a PR-based rollout. That means that the delta between your local environment and the production cluster is just 1 PR away. As well with GitOps, we have the feature of automatic reconciliation. With the GitOps tools, they're actually going to watch a repository, and if new changes are identified, they're going to be extrapolated and applied to the cluster straight away. But more importantly, with GitOps, we have a version state of our cluster. That means that we have historical data points when we know our application was up and running, and using Git commands, we can easily revert to that state. When you're looking into the cloud-native ecosystem, currently this area is led by tools such as Flux and ArgoCD. Flux currently is an incubation CNCF project and has been donated by Weaveworks, while ArgoCD has been donated by one of our end-user organization, which is Intuit. It's worth to mention currently that Argo is undergoing a graduation vote, so hopefully we're going to see this tool as one of our graduated projects as well. By default, with Argo and FluxCD, we're going to have different functionalities and different features. With Argo, we have the support for multi-tenancy. That means that with one ArgoCD instance, we'll be able to manage the applications for multiple teams and multiple domains. As well, Argo has support for multiple configuration tools. So pretty much how we define the state of our application. By default, we're going to have support for plain YAML, but we can use configuration managers such as Helm, Customize, and even JSONet. As well, ArgoCD has support for deployment to multiple clusters. That means that from one instance of ArgoCD, you'll be able to propagate your applications across different clusters and different regions. And a cool feature of our ArgoCD is the user interface or UI. So pretty much in addition to deploying your resources, you're actually going to have a graphical representation of these resources, and you'll be able to explore those states within the UI as well. Flux, on the other hand, is a more lightweight tool. Pretty much it has one installation per repository. And this by default removes the support for multi-tenancy. If you'd like to manage multiple applications with Flux, pretty much you're going to have multiple installations of Flux within a cluster. As well, Flux has support for multiple configuration tools. So by default, you're going to have the plain YAML, Helm, and Customize. And a cool feature for Flux is the fact that it supports the automatic deployment of new image versions. That means that if you have an application and there is a new version for that particular application, Flux will be able to identify it and roll it out within the cluster. At this stage, we have a brief introduction of the cloud-native tools that support the GitOps strategy. However, I would like to deep dive a bit more into how GitOps can be used in real case scenarios. In this particular section, I'm going to focus how FluxCD can be used to automate the infrastructure provisioning of a cluster by using ClusterAPI. I would like to introduce ClusterAPI just to make sure that we have the ground knowledge on components for ClusterAPI set up. So currently, ClusterAPI provides a set of declarative APIs for cluster creation, configuration, management, and deletion across multiple cloud providers. When we refer to ClusterAPI, we refer to C Cluster Lifecycle, which had its first initial release in April 2019. Since then, it had 2 more releases, and currently it presents a V1 Alpha 3 endpoint. I was mentioning the ClusterAPI integrates with multiple cloud providers, and currently we have a dozen of them, from which some of the major cloud providers such as AWS, Azure, Google Cloud, and many more. As well, the metal provisioning of a cluster is currently supported by Packet and Tinker. And we even have support for Chinese providers such as Tencent, Baidu, and Alibaba Cloud. Let's look in a bit more detail how ClusterAPI works. Supposedly, you'd like to provision a set of clusters in different regions, different cloud providers. The first step is to provision a management cluster. For testing purposes, it is recommended to use Kind, which pretty much is a Dockerized version of Kubernetes, and it's quite lightweight, and you can even run it on your local machine. If you'd like to use ClusterAPI in production, it is recommended to use a fully fledged Kubernetes cluster, and this is because it comes with a more sophisticated failover mechanism. Once you have our management cluster up and running, we'll require the dependencies installed on it, which are represented by the controller managers. And currently, we have 3 sets of controllers that we require. One for ClusterAPI CRDs, for custom resource definitions, one for the bootstrap provider, and one for the infrastructure provider. ClusterAPI introduces 5 new custom resource definitions, and we'll require a controller for each of them to make sure that we can add, remove, or reconcile any changes to it. The second set of controllers are going to be the bootstrap provider, and this is the component that translates the YAML configuration into Cloud Init script, and it makes sure to add the instance to the cluster as a node. Currently, this functionality is supported by kubeadm and Talus. And the last set of controllers are going to be the infrastructure providers. And this is the particle which actually interacts with the cloud provider API and provisions the resources, such as instances, VPCs, subnets, security groups, and many more. And of course, we're going to have a controller for every single cloud provider. Once we have our controller managers up and running, we'll be able to provision our target clusters. And these are going to be the clusters we will provision or deliver to our engineering team to place their application on top of. These are going to be the clusters that the customers will interact with when consuming a product or a service. Now, I've mentioned that ClusterAPI introduces 5 new custom resource definitions, but more importantly, this enables us to represent our infrastructure as code using YAML. So the first resource that we'll require is going to be a cluster resource. And this pretty much takes care of the networking components for a cluster. We'll be able to specify the CIDR for our pods or any DNS suffix if we have any. The cluster resource by default is going to be associated with the control plane resource. The control plane resource allows us to declaratively manage a set of master machines. As you can see here, we have our machine resources on top of it, which is pretty much the configuration for a node or an instance. We'll be able to define settings such as the instance type, the version of Kubernetes, and many more. Once we have our cluster and control plane configured, we might require to have a data plane. So these are going to be the worker nodes we're going to place our application on top of. Usually this is going to be managed using a machine deployment. A machine deployment resource is very similar to a deployment. Pretty much it comes with a very powerful rolling out strategy between different versions of machine sets. Machine set is very similar to replica set. It will make sure that we have an amount of machine resources up and running at all time. And lastly, we're going to have the actual machines or the actual instances, which pretty much will define our nodes within the cluster. But the role in this case is going to be the worker nodes. Before I move forward with the light demo, I would like to showcase the current setup that I have. Now, the ClusterAPI completely introduces a new concept of cluster as a resource. We'll be able to define our infrastructure using YAML manifests. Once we have our manifest, we'll be able to store it in a GitHub repository. So pretty much we'll be able to have these historical data points of different versions for our manifests. And we can either introduce an extra layer of abstraction or a configuration manager such as Helm or Customize. In this particular demo, I'm going to use Helm. So pretty much we'll be able to parameterize our manifest using a Helm chart. To deploy all of these resources, I'm going to use Flux CD. So pretty much if we have any new changes to our manifest, they're going to be identified by Flux and applied straight away. Now, the ClusterAPI components and Flux CD are going to be installed on the management cluster. And the management cluster, pretty much from this point, will be able to provision our target clusters. It is worth to mention that for this demo, I have provisioned the target cluster, mainly because it takes around 10 minutes to have it up and running. However, in the demo, I'm going to change the amount of worker nodes we have within our cluster. So for that, we're going to change our YAML manifests and through the Helm chart. These changes are going to be identified by Flux and applied to the target cluster straight away. Before I move forward, I would like to introduce the 2 sets of configuration that Flux CD requires, so custom resource definitions. The first set of configuration is to define the location of our manifest, so where we have the desired state of our application, or in this case, the desired state of our infrastructure. And the second set of controllers are going to be the release strategy, so how we would like our components to be deployed. So in this particular demo, I'm going to have my Helm chart being stored in a Git repository. So this is going to be under the source controller ownership. As such, I'm going to have a Git repository resource with the name copy AWS. In the spec section, you see that I have an interval of 30 seconds. So Flux is going to monitor this repository every single 30 seconds. And if new changes are identified, these are going to be applied straight away. And lastly, we're going to actually define where our manifests are living. And in this case, it's going to be within the ClusterAPI Helm chart repository, and we're going to check out on the main branch. As mentioned, the second set of configuration is going to be the strategy for releasing our components. Since I have a Helm chart, I'm going to use the Helm controller capabilities. As such, I'm going to have a Helm release resource with the name copy AWS. I'm going to have an interval of 30 seconds as well, meaning that if new changes are identified to our Helm chart, we're going to apply them straight away, well, within 30 seconds. And then in the spec section of the chart, you'll be able that we reference our Git repository that we defined in the earlier slide. So here we defined our repository, but more importantly, we represent or we specify the relative path towards our chart. In this case, our chart is located under the charts/copy AWS folder. And towards the end, we can see that we select a particular values file for our Helm chart. So pretty much what input variables we should have for this chart. And in this particular case, all of the variables are going to be stored within the values/demo.yaml file. And without any further ado, let's see how this actually looks in action. So as mentioned, currently I have a Helm chart in this repository. I have a Helm chart for templating all of my ClusterAPI components. So if I look within the templates folder, I'll be able to see all of our YAML manifests. So for example, we can go to cluster resource. So we have a cluster resource. We define a CIDR for our pods. We define or reference our control plane and infrastructure reference, which is going to define it as an AWS cluster. However, in this demo, I would like to change the amount of replicas we have for our data plane. So this is going to be managed by the machine deployment resource, as we've seen in the slides. And as you can see here, I have a templated version or representation of the amount of replicas. And this is going to be overridden by the values input file. And if I go to my terminal, currently, as mentioned, I have the target cluster being provisioned, and currently it has 3 master nodes and 3 worker nodes. So in total, we have 6 machines. And towards the bottom half of the view, you'll be able to see the logs from the Flux source controller. Now, without any further ado, let's introduce some changes. So if I go to the values-demo file, I would like to change the amount of replicas from 3 to 5. As well, with Flux, it is important to change the chart version. And this is because this is the only way for Flux to identify that there has been new changes to this particular Helm chart. So we're going to change our chart version, and then we're going to commit all of these files. So if I do a git diff, I'll be able to see that I've changed the chart version and the amount of replicas for our workers. Let's commit these changes. And I'm going to use a demo commit message, very meaningful, and let's do a git push. Cool. And now we have a new commit that changes the amount of replicas for our worker nodes. And we should see soon enough, or within 30 seconds, we should see that this is going to be identified by Flux. We see that the source controller already has seen the new commit, and more importantly, we see that 2 new machines are currently being provisioned for our data plane. And we can further confirm that if we go to the AWS console and if we do a refresh, soon enough, hopefully we're going to see 2 new instances initializing. Here we go. So we have 2 new instances being initialized to be added to our cluster. And if we wait for another minute or 2, we'll be able to see that these machine resources are going to be in an up and running state within the cluster. And this is pretty much how can we automatically roll out changes to our infrastructure using the power of GitOps, and in this particular case, the power of FluxCD. Going back to my slides. The second use case I wanted to showcase when it comes to the GitOps model is how can we propagate our applications towards the edge. In this particular case, I'm going to focus on KubeEdge and ArgoCD. I would like to start with a short explanation of what KubeEdge represents. KubeEdge is built on top of Kubernetes, and it provides synchronization for metadata application and networking synchronization between the cloud and the edge. Using KubeEdge allows us to have seamless communication between the cloud and edge components. What it actually means is when you deploy your application, you just need to interact with the cloud side. And the application is going to be propagated towards the edge, and it's going to be completely abstracted from the user. As well with KubeEdge, we have the edge autonomy. That means that if the cloud side is down, or there is a misconfiguration, or the connection is lost between the cloud and the edge, the application on the edge is still going to be up and running independently. And KubeEdge as well has been constructed to be running on low resources such as CPU, memory, and bandwidth. Let's look into the KubeEdge architecture briefly. So currently there are three main areas that I would like to identify here: cloud, edge, and the devices. It is worth mentioning that the edge and the devices here actually represent the edge. However, the devices are the physical components that are with the end users, and I would like to differentiate that. When you're looking into the cloud side, we're going to have a Kubernetes cluster, but more importantly, this is going to be integrating or communicating with the cloud core components. The cloud core components will communicate with Kubernetes, but at the same time, it will make sure to proxy any requests to the edge using a WebSocket. On the edge side, we're going to have the edge core components, which communicates with the container engine runtime and with the MQTT client. Currently, we'll be able to manage our containers on the edge using a runtime such as Docker, Containerd, CRI-O, or Vertlet. As well, the edge core components are going to talk with the MQTT client, and this will pretty much ensure that we synchronize the state of the device with the desired state that we have on the edge. As well, before I move forward with the actual demo, I would like to introduce an overview of the current setup. So in this demo, I'm going to have two nodes, one of which is going to represent the cloud, and the other is going to represent the edge. On the cloud side, I have a Kubernetes cluster up and running, and I'm going to have the edge core components, cloud core components already installed. As well on this side, I'm going to have ArgoCD installed, and we'll be able to interact with the UI as well. When you're looking into the edge node, we're going to have the edge core components already installed, and we're going to use Docker to manage our applications. That means that any applications that are going to be pushed towards the edge are going to be run and identified as Docker containers. And before we move towards the live demo, I'd like to introduce the ArgoCD customer source definition, which in this case is an application. This particular resource is used to define where we store our configuration, so pretty much the source, and we define the destination, so where we'd like our components or infrastructure or application to be deployed. So in this particular case, we have an application CRD with the name Nginx Edge, and it's going to be deployed within the ArgoCD namespace. If you look into the spec section, I have trimmed the output for destination just to shorten the output within this slide. And towards the end, you can see the source. And currently, we define that our manifests are stored within the KubeEdge ArgoCD demo repository, and it's underneath the manifests folder. And you can see this defined in the path variable. And towards the end, we can see that we have a sync policy, which is set to automated. So pretty much any new changes that are going to be identified are going to be applied to the cluster straight away. As well with ArgoCD, we have an option for manual synchronization, and this is useful if you'd like to validate the changes before applying them. And this is the time to move towards the second demo. So if I go back to my terminal, as mentioned, currently I have two nodes, one of which is going to represent the cloud, and the other one is going to represent the edge. On the cloud side, as mentioned, we have a Kubernetes cluster up and running, which means that we'll be able to use kubectl commands to interact with it. So if I do a kubectl get pods, currently I see that I have no pods, no applications up and running. However, because I have KubeEdge already installed, I can get the nodes. So currently you can see that I have two nodes present or available for this cluster. The first one is the master node. So this is the actual node which comes with the Kubernetes cluster that I have installed. However, the second one is the node which is an agent on the edge. So this already has been added to the cluster with the edge core components. Now let's deploy something to ArgoCD. Before I move forward, I would like to showcase our application CRD, and pretty much everything we had in the slide. We have an application CRD with the name Nginx Edge. Here we can actually see the definition of our destination, which is the current cluster. So we deploy our application to the current cluster, and you can see the source pretty much where we store the representation or the state of our application. If we go into GitHub, we'll be able to see that within the manifest folder, we have an Nginx deployment. Pretty much this is a very simple deployment over here that deploys one replica of Nginx in the Alpine version. So pretty straightforward. And I as well can interact with the ArgoCD UI, and currently I can see that I have no applications defined or deployed. So if we exit this file, we can apply our application CRD by using the kubectl commands. So I'm going to use the kubectl-f apply our ArgoCD application. Going back to the UI, we can see that application has been created and it's automatically synchronized. If you click on it, we'll be able to see that we have our deployment for Nginx with one pod. So we have one replica of our application. Going back to the terminal, I can do a kubectl get pod, and I can see that I have one replica of our Nginx application up and running. However, if I choose or select a wide output, I'll be able to see that our application has been pushed towards the edge node straight away. And you can see this has been happening 30 seconds ago. And we can further confirm that by looking into our edge component. So as mentioned on the edge, we don't have Kubernetes installed. So if I do a kubectl command, we'll not be able to identify it. And this is because on the edge, we manage our containers using Docker. So if we're doing a Docker PS, we'll be able to see a bunch of containers. We're going to have a set of them which are going to be related to the load balancer. Currently, we're using Traefik to provision those. However, I would like to draw your attention towards these two containers, which have been created just 1 minute ago. And the first one is pretty much our Nginx application container, which is running, and that one is going to be the post container. And this is pretty much how we'll be able to push our applications towards the edge by using the power of ArgoCD. Going back to the slides. So this concludes the talks and the examples I wanted to give today. We started by introducing the cloud-native GitOps tools such as ArgoCD and Flux, but more importantly, we deep dive into real use cases of using GitOps model. As such, we looked into how can we provision our infrastructure with ClusterAPI and FluxCD. And as well, towards the end, we looked into how can we push our application towards the edge components by using tools such as KubeEdge and ArgoCD. And this has been possible because GitOps at the moment is the moving force that redefines the deployment of cloud-native components. But more importantly, it is based on the declarative, automatic, and reliable fundamentals. If you have more questions about today's talk, please reach out. I'm going to write a Medium article with more information of how this current setup has been done, and you'll be able to follow it with more details. As well, if you have questions around this talk, I'm going to be available on social media to answer them, such as Twitter and LinkedIn. Hello, everyone. Hopefully you can hear me well. Thank you very much for attending the talk, and thank you very much for some of the questions, and I've seen them in the chat and in the Q&A box. I'll try to answer them. I have only 1 minute, but if you would like to have more questions, do reach out on the social media. I'm more than happy to answer most of them. Before I answer some of the questions, I want to specify that for the FluxCD, there's actually the multi-tenancy feature has been developed in the past months, so definitely do check it out as well. It's something that has been, again, contributed by the community quite strongly, so definitely recommend to check that. There is about ClusterAPI and how it handles the dynamic changes when it comes to Cluster Autoscaler. So this is something that the community has been working on, for the ClusterAPI community has been working on. It's fully supported, so the only thing you need to do is to enable the Cluster Autoscaler, and it will be able to apply or pretty much scale your cluster up and down, irrespective of the cloud provider. So definitely do check that out as well. And I have only 30 seconds left. There's one question around what is the best tool in terms of between ArgoCD and FluxCD, when to use one and then when to use the other. Here, I would definitely recommend to really understand your setup, and if you actually need to use a tool such as GitOps, and based on the functionalities that every single tool provide, I would suggest to use that in-house. Unfortunately, I don't have time to go further into details around these questions, but again, if you have more questions, I'll be around on social media, so do reach out there. And I think this is the time up. Thank you very much for attending.